Right.
Well, there's the title. Over to you, Mike.
Am I off? Thank you very much. Well, thank you very much for asking me to speak. I'm sorry I've been a semi-detached member of this programme, but I've had a little bit to do in King's College also, but also I've been away in Australia, so forgive me for being absent. And forgive my voice.
A neutral logo.
Sorry?
Neutral logo.
A neutral logo, yes, yes. It's very low resolution, actually, I realise. I must get a better one. I just want to talk really about a lot of what I'm going to talk about is work I've done recently in the last few years, mostly with David Hughes, some with Benjamin Favier, and some with David Galloway, who I've been visiting in Australia. But I want to set the scene, for those of you who are not dynamo theory experts, just reminding people what the dynamo problem is and how it applies to the sun, for example, how people have tried to produce simplified models of the dynamo process using so-called mean field electrodynamics, what's wrong with that, attempts to understand what's wrong with that, and then finally give up the ghost and think about some other problem completely. So that's my plan. So let me just remind people very quickly, the dynamo process, it's the production of magnetic flux by fluid motion. In a perfectly conducting fluid, the flux through any material is preserved, according to Faraday, or you can think of magnetic field lines as material lines. You can increase magnetic energy by stretching, but you can't change the magnetic flux. So in an astrophysical body, for example, you want to increase the magnetic dipole moment. You can't rely on stretching to do that because the total flux out of any surface is unchanged without diffusion. So the dynamo problem is a problem because you can't just think about infinitely conducting fluid. So you have to have ohmic losses. You have to have ohmic losses in real fluids decrease the energy, but they do permit reconnection of magnetic field lines. The field lines become detached from the fluid, and you can in fact get increases in flux. But it's a complicated process because if you want to stretch your fluid, which definitely increases energy in a good conductor, in a finite space, you also have to fold it. It has to be put back where it was before. And so you have stretching and folding. The folding leads to increased gradients. The gradients, short length scale variation of the field, increases the ohmic losses. So there's a balance to be struck between stretching and folding for highly conducting fluids. And in this game, we ignore the displacement current in Maxwell's equations, and therefore we don't have any electromagnetic waves. And if you then look for Ohm's law in the moving fluid, you then can eliminate the electric field and write an equation, a closed equation for the magnetic field B, which depends on the velocity here. So this first part, if that was without this second term, that is Faraday's law, if you wish. The equivalent statement is that magnetic field lines move with the fluid. So this is an induction effect. And this is diffusion. And there's a one parameter here, which is the magnetic Reynolds number, which is the typical velocity scale, typical length scale, divided by eta. Eta is a quantity with the same dimensions as kinematic viscosity, which is inversely proportional to the conductivity. So highly conducting fluids have small magnetic diffusivity.
Much less, you mean much greater than nu?
I do. I really do. Eta is enormous compared to nu. It's not 10 to the fifth times
In the Earth,
in the Earth. In the sun, who knows?
even in the sun.
Well, no, it depends where you are. It's very hot everywhere, so I haven't been there. But certainly on Earth and in the laboratory, eta is very much bigger than nu. And it turns out that this parameter measuring, so Rm measures the strength of induction, if you like. So large Rm means highly conducting. Rm has to be sufficiently large for self-sustained fields in finite bodies. And so we're faced with the difficulty immediately that any terrestrial dynamo, and indeed a dynamo in the sun or the laboratory, has huge Reynolds numbers. So you can imagine that it's highly turbulent. This has been a formal problem which I haven't worked on. It's very hard to get large values of Rm in the laboratory. So a cubic meter of mercury moving at 1 meter per second has a magnetic Reynolds number of about 1. There are not very many cubic meters of mercury about, let alone liquid sodium, which is easier to deal with, but hot and potentially reactive. So you have to be careful to get large RMs. And as I'll say in a minute, in the laboratory it's quite hard to get growth of magnetic fields. And numerical experiments, which are better than the laboratory experiments, can't reach astrophysical values. So we're actually in a funny game that we know the equation, more or less, but we can't reach the right values of the parameters to understand fully what's going on in the cosmos. So let me just remind people, and I hope this is going to work, because I can't see the cursor anymore. There we are. This is a movie made by Galileo. Whoops. No, I'm not joking. He drew all the pictures. Somebody put it together into a film. Jack Eddy, I think it was. So he drew these sunspots, which you saw on the surface of the sun, and he drew them every day. And I'm not sure how to repeat this. So, there we are. So you can see not only that the sun is rotating about that sort of axis, but also that these things change in time. And a modern way of looking at sunspots on the surface of the sun is to look at a magnetogram where the black and white correspond to polarities of magnetic field. That's how you do it. And then you play. Well, that's the plan anyway. Yes, there we go. So this is it's observed, modern day, 1998, and you have black and white, which are positive and negative polarity of magnetic field. And you can see discrete zones of magnetic activity. There's some gross similarity between the two hemispheres. The thing that's interesting here is that the white bits on the top half are on the right, whereas the white bits on the bottom half are on the left. So this means that sunspots come in pairs because they're seats of intense magnetic field that bubble up from below the surface. And what goes up comes down, because div B is 0. And so you get two spots, or two magnetic areas with different polarities. And in the northern hemisphere, for example, say the northern polarity is ahead of the southern polarity, and it's the opposite in the other direction. So that suggests that there's a deep-seated magnetic field which is antisymmetric about the equator of the sun. And all this is all evolving in time. So these things change in time. They have a lifetime of about a month. But there's a real coherence in the system, because if you track the appearance of sunspots over time, and this isn't quite up to date, but I searched on the web last night and I couldn't find a more recent picture like this. I don't know why not. Then you see a persistent and coherent pattern of sunspot activity moving towards the equator during each 11-year period, approximately every 11 years. But every 11 years, the polarity of the leading spot changes in both hemispheres. So it's really a 22-year cycle. So you have an oscillating magnetic field, which is dynamically active. You can see this is not a regular linear process. Every cycle is a bit different. There's lots of noise. And in fact, the most recent cycle, which is just off this diagram, is very much weaker than all the others. In fact, the weakest for 100 years, comparable to this one here. So there's modulation of activity. But what's interesting to me is that there is coherence. So somehow, the sun, which is convecting on very small scales, you can't see the convection here because this is just magnetic fields, but the scales of convection are tiny compared to this picture, smaller scales. And yet, the sun knows when to reverse its field. And it's doing the same thing in the two hemispheres. So there's some global process going on. But it's on a much bigger scale than any of the motions we can see at the surface. So it's a bit of a mystery. And there's also modulation, and I can't resist this picture, which is a wonderful drawing of the Thames in 1684. In fact, it says 9th of February, 1684. And you're looking at the north bank of the Thames. This is the temple here, and one or two other buildings, Arundel House, which I think is still there. And this is all ice, you see, and they're all doing strange things on the ice. And here seems to be some dogs killing a cow. It isn't quite clear what's going on here. There seems to be an animal tied to a post being worried by dogs, rather unpleasant. That was England in the 17th century. Other people doing less noxious things. But the frost fairs on the Thames were familiar events, in fact, even until the very early 19th century. And this coincided with the period, at least this coincided with the period when there were no sunspots at all, around here, 1680 something. And people were looking for sunspots, and they'd found them earlier with their primitive telescopes, and they stopped finding them, and then behavior took off again. And then there was a minimum in activity, a relative minimum, around 1800. And then since then, things have not changed enormously. So this shows it's a fully nonlinear dynamical process. It's very easy to construct very simple differential equation models that have this sort of modulational behavior. I'm not sure it teaches you an enormous amount about the processes, but it's not a surprise that you get this sort of modulation. On the other hand, if you look at proxy data, if you look at tree rings and carbon-14 in tree rings and beryllium-10 in ice cores, these are signatures of cosmic ray activity. So when there's more cosmic rays, you get more radioactive carbon, more radioactive beryllium. And low solar activity leads to more cosmic rays. And so there's an anti-correlation, so you can plot solar activity into the distant past. I haven't got a picture, I'm sorry. But it shows that there are modulations. You can pick out the 11-year cycle if you're clever, 22-year cycle, and you can also see modulations in that behavior with periods of about 200 years, which is not so different from what is going on right now. So it's probable that solar activity has continued in the past, but that the occurrence of sunspots depends sensitively on the details of that process. I'm not going to talk about that today, but it's an interesting question. So we have a fully dynamic process which is highly coherent. How are we to reconcile that with the different scales of flow? And just to say, this nice picture from Carey Forest just shows you how far we have to go. Here's the sun, here's the Earth, here are experiments with liquid sodium, here are numerical simulations, and there are new experiments that Forest is carrying out with using a plasma, but even these are a long way from the parameters appropriate to the sun. And here's the magnetic Reynolds number and the Reynolds number. So to even get to the Earth, we're having some trouble there. I'm not going to talk today about laboratory dynamos, but there's been a lot of trouble generating magnetic fields in the laboratory. So, but many working laboratory dynamos feature helical flows and small values of the magnetic Reynolds number on the smallest scale. Okay, so they have a big apparatus, small scale velocity. The RM, the magnetic Reynolds number on the smallest scale of flow, is small. So I said that the magnetic Reynolds number had to be large, or at least order 1, for dynamo action. Well, as long as the magnetic Reynolds number on the largest scale is large, and the product of the RM on the smallest scale and the RM on the largest scale is of order 1, then it's possible to get growth of magnetic field, and I'll show you. And this is called mean field dynamo action. So the field is generated on a scale much larger than the scale of the energy containing flow. And the Karlsruhe dynamo, which is a dynamo in which fluid is forced through helical pipes, you do get a large-scale field on a scale much larger than that of the pipes. But unfortunately, although that's very interesting, in nature, the magnetic Reynolds number is large everywhere, even on the smallest scales. It's vast, even on the scale of the solar granulation. There's no place where RM is small that is a plausible scale of motion on the sun. But is there any way of simplifying the equation so that we can learn something about coherent dynamo activity? There are two sorts of dynamo. It's important to keep the distinction in mind. It's all the same equation, just different mechanisms. So the so-called small-scale dynamo, fluctuation dynamo, comes from sufficiently vigorous flows with complex structure. So magnetic energy is enhanced by stretching, and there's also folding and diffusion, and that leads to cancellation of the magnetic field. So there are two effects going on at the same time, and if you choose your flow correctly, then you can find that the stretching will dominate the diffusion, and you can have growth of the magnetic field. The magnetic field grows on a scale like the scale of the flow, and perhaps even smaller. I'll show you an example. It's not necessary to have any broken mirror symmetry. The idea that you have to have, I talked about helical flows. When we come to midfield dynamos, helical flows are important. but not for this process. You can easily construct a dynamo in this way with no broken mirror symmetry on average, or even locally. Then there's a different process, so-called mean field process, which works even when the flows are very weak, provided you have a very large scale to operate in. There's a distinguished limit here. The small scale flow interacts with the small scale field, which is induced. So you have a large scale field, small scale flow, that bends the magnetic field lines on the small scale. Then you have a small scale magnetic field induced, and you have a small scale flow. And that, the electromotive force, the inductive force, the EMF, is to do with the product of the flow and the field. And so you can have two small scale fields with a large scale. When you multiply them together, you have a large scale average. And if you can show that the EMF that's produced in this way has a component parallel to the large scale magnetic field, then you can get growth of the magnetic field on the largest scale. But chirality is essential for this. This is the alpha effect, so-called, and chirality is essential for this effect. There are other mean field effects, but they're much less effective. And normally, in models, for example, of the sun dynamo, you assume that you have the leading term, which I will describe in a minute, for which lack of mirror symmetry is essential. So it's a different process, very different process from this one. So quickly, the mean field concept. We have flows and fields on small and large scales. So let's invent an average and just assume that the average obeys the usual rules. So B is its average plus fluctuations. The average of the fluctuation is 0. The average of the average is the average, and the average of the sum is the sum of the average. So we can split the equations into two parts. So there's no approximation here. This is the mean part. I haven't defined what this average means. It's just a symbol. It could be an average over the azimuth. It could be an average over scales intermediate between the turbulence and the large scale. Any suitable average, if one is to be found. And the equation for the mean field involves this term which involves the average of the fluctuating fields. So U is the fluctuating velocity field, B is the fluctuating small scale magnetic field, and their average could have a large scale component. And then you subtract this from the full equation, you get an equation for the fluctuating field. This is all very straightforward. And then you say, we call E the mean electromotive force, and if you put this in, if you can find B as a function of big B, then you can close the equation for the average of B and get a closed model. And actually, as an aside, you can do a similar decomposition for the momentum equation. I haven't talked about that. I assume that we know what the velocity is, but if we're doing a real problem where the magnetic field exerts forces, then there are Reynolds stresses produced in the momentum equation on the large scale, and there are also magnetic Maxwell stresses produced. And if you want to find a fully self-consistent dynamo, including magnetic forces, you can't be just doing this. You have to look at the two equations, the momentum and the induction equation, and produce mean field coefficients together. That's the subject of a whole other talk, which I haven't got time to deliver this morning. So what about the mean EMF? Well, in principle, and now you have to pay attention, all right? Find the deliberate mistake. In principle, be expressed in terms of B through the equation for little b. It's plain that because the equation for little b is a linear functional, there's a forcing term which is proportional to the derivatives of the average of b, then clearly little b is a linear functional of the average of b. And there are several assumptions of those which is involved in that statement. But we'll come to those in a minute. But let's assume everything is all right, that we have a local relation in space and time between the fluctuating field and the average field, and then that we could perform the average, get the mean EMF, and it's still a local description. So we have the mean EMF can be written in this way, where these quantities here don't depend on the magnetic field, but only on the nature of the velocity field. And this is a tensor, a so-called pseudo-tensor, which would change sign under reflection. And it's because of that that if we have mirror symmetric flow, then this quantity is 0. So chirality is essential. This is like an anisotropic diffusion, and in an isotropic situation, it looks just like an isotropic vector, and this quantity looks like a curl. So this is like an extra diffusion, although it may be negative as well as positive. This is a new term where the EMF is parallel to the mean magnetic field. That's if the motion is isotropic but not mirror symmetric. So there are several assumptions here, and the worst one is that we assume that little b owes its existence entirely to big B. Well, we go back and look at the equation. So this equation is linear in little b, and there's an inhomogeneous term here. So if you could solve this equation, then there would be a term which scaled with b averaged. But there might also be a term which is independent of b averaged, because there might be a small-scale dynamo. Okay, a small-scale dynamo doesn't have any mean field. So you could put b bar equal to 0, just look at the fluctuations of b on the scale of the small-scale flow, and you could get a small-scale field just growing independently of the existence of the mean field. This is always ignored. Right?
That would be the last term.
No, that's just, this is still linear. This whole thing is still, it involves little b. It's this one is the forcing. This is inhomogeneous as regards little b. So if you strike that out, in principle, you can still solve this problem. I mean, there are so this is a serious worry, because in real life, on the sun, there's no doubt small-scale dynamo action everywhere. And in order to understand what's going on, I believe, and I'm not going to talk about this in detail because I've got no time, we've got small-scale dynamo action everywhere, so it's not obvious that you can even write down such an ansatz, because there may be terms in this E which are independent of average of B. So then it becomes a different problem completely. But let's assume, for the time being, that we can do this. That I want you to keep in your head. This is a big assumption, actually. And that, I should say that if things are isotropic, then of course, this is an isotropic tensor and therefore reduces to a scalar. In principle, this doesn't have to be a symmetric tensor. If this has an antisymmetric part, then the antisymmetric part corresponds to an EMF perpendicular to B. And if you remember, the induction term is curl U cross B. So curl E is curl of something perpendicular to B. So it's like the action of another velocity. So there are two sorts of possible things that can happen here. One is you get EMF parallel to B, which leads to growth of the field. And the other is you get, like a velocity, a mean effect, which we call turbulent pumping, which pushes magnetic field along in a situation where you have anisotropy, and you're allowed antisymmetric components of the alpha tensor. So how do you model the large-scale dynamo using the alpha effect? So this is old stuff. There are two main ways of thinking about things. There's a differential rotation of the sun, which is obvious to the naked eye, actually. The sun rotates about once a month, but faster at the equator and slower at the poles. Suppose you have a meridional field on average, and it's acted on by a velocity which is biggest at the equator, then this pulls out the magnetic field, at least for a while, into this sort of structure, and you can see now that you've produced some azimuthal field, which is antisymmetric about the equator, which is just what we appear to observe in the sun. So this process, which is very robust, is no doubt an important mechanism in producing zonal field. But as you'll see, in order to make the poloidal field grow, you need some process which converts this zonal field into poloidal field. And this is the alpha effect that I just talked about. And here's a physical representation of it. You start with a mean field B. You act on it with a velocity upwards, and so you have a sort of bulb here. Then you twist it a bit, because you have a chiral, the field has helicity, a correlation between velocity and vorticity. So it has chirality. You lift and you twist. You twist it a bit, then there's always a component of the net EMF. Now you can reconnect the field, so you have the original field plus this thing. This gives you a current, which is anti-parallel to B. It may give also one parallel to B, but we won't worry about that. Here's a current which is anti-parallel to B. And so this effect is the same as the alpha effect I just talked about. Also, it tells you what the sign ought to be of the effect. And so if you put these two together, then you can write down some closed equations. So here we are. This is the same equations I wrote down before. And suppose B, now we look for axisymmetric mean fields, and you can write B as the curl of a vector in the phi direction. That's the poloidal field and a toroidal field. And you can do the same with a velocity field. Let's assume that. This is the mean of U. And then you can write down two coupled equations for A and B, which here is the differential rotation term, the gradient of the angular velocity. That's the angular velocity there. And here's this term involving the alpha effect. There's also another alpha effect term in here, but it's generally not important. This is the crucial term which couples the A equation to the B equation, whereas this term here couples the B equation to the A equation. So this is a closed system which in principle can lead to growth of the field. And this is called an alpha-omega dynamo. Alpha here and omega here. It's the beginning and the end of dynamo theory. And if you solve these equations, it's quite easy to find solutions to the equation if you choose alpha appropriately. And remember, we don't know how to calculate it. So we choose exactly as we like, but we might think it's odd about the equator for reasons to do with the fact that you need chirality, and the chirality is assumed to come from the rotation of the sun, and so it's natural to think of alpha as being odd about the equator. And if that's the case, and we know that omega is even about the equator, then there are solutions which have the nice parity, where A is even and B is odd, and another one where A is odd and B is even. This is what we see today. So you have a dipoles. So here you see the poloidal. I've got to get the right way around. Is this right? Yes. So this has a field which has a dipole moment at large distance. This is the poloidal field. This is the toroidal field, and it's odd about the equator. It's a very old calculation. And here's one of the opposite parity, where this is a quadrupole field at infinity if you follow the arrows, and the toroidal field is even about the equator. And if you choose your model carefully, and you make this assumption about the parity, and you make alpha negative in the northern hemisphere, then you can find exponentially growing waves propagating towards the equator. Done. Solve the solar dynamo problem. And we found the answer as this coherent effect, which leads to propagation of activity towards the equator. And then you fiddle around with the numbers here to make the cycle last 11 years, and then you, well, you're famous, because it is the only, at the moment, it's the only show in town that, and it has been for many years, that yields the result that you're looking for. But let's be careful about this. How do we calculate alpha? This is a paper from Moffat's book, from Keith's book, in which he noted very early on about the difficulties that could arise from the picture. So he told me yesterday that he was preparing to defend the alpha effect. This is him here, so he's the chief witness for the prosecution. So what he said was, and it's entirely correct, that the Parker picture, in which you have a twist like this leading to a current anti-parallel to the magnetic field, is predicated on the idea that the twist is small. Right? Now that is true. It's always true when the magnetic Reynolds number of the flow at the small scale is small, because then the field is hardly changed at all, and the angle, whatever you do, you have some event which hardly moves the field, and the twist is always less than pi by 2, and you always get a component of the current anti-parallel to the field. But when that's not true, and it's not true probably in real turbulence, it's certainly a moderate magnetic Reynolds number, the relationship between the twist in a rotating fluid and the push-up and the time of any event is not known, then you could have any number of twists. Right? So twist it twice, the current goes the other way. So what's the sign of the alpha effect? If you could have an arbitrary set of twists, well, it's very difficult to know. So you can do a very simple model. I haven't got any details here, but you can imagine a very simple flow, which consists of stationary fluid and a cylinder of fluid, which is rising and twisting. Very simple. And you can actually, so you can calculate the EMF due to that event. So it's an exact analog of this. And you can then assume that you have a lot of these events which have arbitrary angles, or arbitrary lifetimes, and according to some probability distribution with a standard deviation sigma. So phi is the average angle through which you twist, and sigma is the standard deviation of those angles. And with some plausible models, the magnetic field, the EMF that's produced, has a form of this kind. So when phi is small, you can see that you get, well, I've made it positive actually, it should be the opposite sign. But, there's no minus sign, I realise now, but it doesn't matter. When phi is very small, then you have a definite sign, SIGN, for the EMF. But when phi becomes larger, especially when you have a lot of variability in the twist, which is likely, then the sign becomes indeterminate, and eventually the effect becomes very small. So if you calculate this object on the assumption that the standard deviation of the angular twist is comparable to the angular twist, I've chosen an extreme example so I can fit it on the page, but the idea is clear. The small phi, you get a good EMF, but then it changes sign, and finally it drops off altogether because the twists become completely incoherent, and they all cancel each other out. And you say, well, that's a very simple model. Let's have a look at real life. So this is a calculation I'm going to talk about briefly soon. And with David Hughes, and what we did here was we put a uniform magnetic field into a convecting layer, so disordered convection. And we calculated the EMF that was produced as a function of time. And then we stopped and did it again. Okay, so it's an averaged EMF. And you can see initially, things rise and it's all pretty coherent, and then it gets completely out of whack. And if you were to plot the average over all these events, it would look a bit like that, I believe. In fact, the similarity is quite striking. And I'm going to be repeating myself a bit, but this goes with these pictures. This is from the calculation I'm going to describe. This is the helicity, the relative helicity in the flow as a function of depth in the layer. Perhaps I'd better just show you the geometry. Very simple geometry. So you have a layer of fluid, heated from below, rotating about a vertical axis, gravity downwards. And then you have convective flow in there. And you measure this quantity, which is antisymmetric about the midplane because of the symmetries. But you can see, and it's different at different values of the magnetic Reynolds number, different values of the Rayleigh number, the heating. But in every case, it's a very well-defined quantity. This is an average taken in x and y, plotted as a function of z. And you can see there's no error bars on here. It's really well-defined. The helicity, the chirality, and the flow is very well-defined. Now, if the normal alpha effect were correct in this regime, then you get very well-defined alpha, because it would just be proportional to this helicity. But it's not. So these are the three components of the EMF, calculated in the same way as this. But now these are averages as a function of time over a long run. And you can see that the lines in the middle are the running averages. Of course, there is a running average, but they're very, very small. This one should be non-zero, and these two should be zero, according to the theory. And in fact, it's hard to distinguish this one from zero, although the eye of faith suggests there is a tiny non-zero component. But the fluctuations are huge compared to the mean. And you might well ask yourself, well, what on earth does the alpha effect mean in this situation? Can you really calculate it? Yes, of course, you can go on for hours, and eventually you'll get an average, and hopefully it won't be zero. But it's hard to believe that such a weak correlation is important in driving the magnetic field. That's a bit worrying. So here's the problem that we looked at. Well, I didn't look at I didn't look at this bit, but David and I looked at something later. This is rotating convection in a layer of the standard Boussinesq convection. Here is the normal equation of motion with Coriolis force, buoyancy force, magnetic forces. It's nonlinear in principle. Viscosity, heat equation, and the induction equation that you've seen before, non-dimensionalized. So it's all Boussinesq, very simple in principle. And then you calculate what's going on, and you can find dynamo action. And here's an example of it. So this is what you're seeing are positive and negative elements of the magnetic field at the top of the layer. This is not moving, in case you're worried. This isn't a movie. When I saw this, I thought, it doesn't seem to be moving, but it's not a movie, that's why. So this is, you can see that the scale of the field is much smaller than the scale of the flow. There's no obvious mean component to the flow. And in fact, inside, this one here, this is looking at the magnetic energy inside. Oh. And you can see again that the scale of the magnetic field in the interior is comparable to the scale of the flow in the interior. There's no evidence here of any mean field effect, even though the helicity is very strong.
That's incompressible or compressible?
It's all incompressible. So I can discuss later why this looks so different from this. Basically, it's because the surface velocity field is not divergence free. That's the field in the surface. So you can see that there's no mean component, and in fact, I'll just show you. I better not. It's too far away. I've got a lot to get through. How long have I got? Because I started late.
20 minutes.
Okay, I shall keep going. All right. So that's no large-scale field. So you might say this is at moderate rotation rates. So you might say, well, how about slightly larger rotation rates? Then maybe we can do some asymptotic theory. This is where Benjamin Favier comes in. He looked, and we looked, at the onset of convection at large Taylor number, so rapidly rotating convection. Now, it's well known in that case that the horizontal scale of motion at onset is small compared to the layer depth. And there is an asymptotic theory due to Soward, which can produce explicitly a mean field term like the alpha effect, which should govern the generation of mean field dynamo action in this layer. We can look at two different planforms, squares and hexagons. As you can see, topologically they're different, and the up and down is similar to this in this case. In fact, they're identical. And here, definitely, there's upward going fluid in detached areas. Now, it's been known again since the Droboszewski-Ufrev paper with the appendix of Moffat that such flows are liable to have a pumping effect. In the asymptotic theory of Soward, there is no pumping effect, and all planforms are completely equivalent. So if you have a small parameter, which is the Taylor number to the minus 1/6 power, sorry about that, and then you have Rm is of the order of the Taylor number to the 1/12 power. This is a danger of where asymptotics can lead you. Then you can calculate in powers of epsilon what the mean EMF should be. And indeed, the leading term looks like this. You have this proportional to the magnetic field, B. And it's proportional to lambda. And then the next term, which is smaller formally, is a pumping term. So it's like a velocity. Now this term is 0 for the squares, but not 0 for the hexagons. But you say, well, it's small. Epsilon is a small quantity. Surely dynamo action is adequately described just using this term. Well, that's not true. So if you look at the growth rate of the mean field dynamo as a function of lambda using this ansatz, which of course is not accurate. It's only accurate when epsilon is really small because there are higher order terms. But just take this as a model. You can see that when epsilon is 0 corresponding to squares, you have perfectly good dynamo action as lambda increases. But when epsilon is really quite small, you have no dynamo action at all. And you say, well, that's just a model. Let's go to the full system. Here's the full system here. You have Taylor numbers of 10 to the 8th, 10 to the 10th, and 10 to the 12th. Okay, so the smallest value of epsilon is 0.01, which is quite small. And the largest one is 0.045. So root epsilon, which comes into here, is 0.2 something here, and 0.1 something here. And what a difference a factor of 2 makes. So for the very, very large Taylor numbers, you do get, indeed, you get dynamo action, which involves a mean field. But for the smaller Taylor numbers, dynamo action is much less efficient. And finally, even though epsilon is really pretty small, no dynamo action at all. For the hexagons, that is. For the squares, everything is fine. You get growth. It's independent of the planform anyway. So this is so this shows you, perhaps strangely, that just taking the leading order term and hoping that it's appropriate to use it to discover what's going on may be highly misleading. And here's an example of where it's highly misleading. Just cutting off here is okay when the Taylor number is vast, but when it's merely very large, it's not okay. Important lesson. Okay, I'm going to have to, I've only got 15 minutes. So we've talked about, you've seen all this already, so I'll pass on from that. Now I want to talk about something else, slightly different. This is some work that was done a few years ago by Youssef and collaborators, who were trying to look for a new dynamo mechanism that didn't involve helicity. So a different sort of large-scale dynamo, which is not fully understood because they haven't done more runs, sadly. What they found, they had turbulence forced by non-helical turbulence, and then they added a uniform shear. So that it's all in a computational box. They added uniform shear, and they found the appropriate ranges in long boxes, a dynamo, a magnetic field that was induced, whose growth rate seemed to increase with the shear rate. And they haven't really got a theory for that. There is a sort of asymptotic theory, but it's a bit dicey actually. But they seem to show this linear behavior of the growth rate with the shear and a corresponding drop of the length scale of the disturbance with the square root of the shear. And they surmised that they had found some new dynamo mechanism which would deliver growth rates comparable to the shear. And in the nomenclature of dynamo theory, that would be a fast dynamo. In other words, the growth, as the shear goes to infinity, if the growth rate scales with the shear rate, then eventually the growth rate becomes independent of the diffusivity, and you have a growth of the magnetic field on a scale of the advection rather than the diffusion. That's called a fast dynamo. But actually, that's not the case. This linear scaling only goes on for a bit, and then it drops off. It must drop off because I've proved it must drop off. So just ignore this stuff on the left. I just want to show you that, maybe now we're getting a bit mathematical, I'm sorry, that in fact you can't have this behavior with S. So I'm assuming that you have a small scale velocity field, little u, and a large scale shear, big U. Oh, sorry, big U and little u are, big U is the whole velocity field, big U is little u plus a shear. So something that in the x direction, which depends on y, and S is the magnitude of the shear. And their claim was that for such fields, if you let S go to infinity, the growth rate of the dynamo would be linear in S. If you divide the induction equation into 3 components, and then you multiply this by bx, this by by, and this by bz, with appropriate boundary conditions, then you can write down 3 equations for the 3 average squares. And you have this stuff here, which is all rather difficult, and you have the bit involving the shear. But then you can bound all these terms in a simple way, and you get these 3 inequalities. So these numbers here do not depend on the shear. They're all positive. They don't depend on the shear. And you have one term here which does depend on the shear. And by analyzing this system, you can see that the growth rate of the dynamo is less than the largest eigenvalue of this linear matrix multiplied by the vector mx, my, mz. And the largest eigenvalue goes like the square root of s. not S. So whatever behavior they found only exists in some region of space and does not persist to the very large S's they would like it to persist to. And that's, I think, quite interesting. The drawback of this theory is that, as you see, it's in a Cartesian geometry, and I haven't yet been able to repeat the trick in a spherical geometry, though I'm sure it must be true there as well. The point I should say is that if you leave out the small-scale flow altogether, then this is not a dynamo, whatever the value of S. You just have a shear. It can't enhance the magnetic field. It can only squeeze it for a bit, and then it will decay. So you've got a non-dynamo field and a fluctuating field, and the combination can give you growth rate proportional to the root of S, but not proportional to S itself. So, but we did think we should put shear into this convective model to see what happened. And so this is the previous convective problem in the layer with a new parameter, S, which is a measure of the shear. And it appears here in these terms now. And we're only going to be interested in the growth rate of small magnetic fields. So there's no Lorentz force, there's no magnetic force in this equation. So this is the same model, except we've added this new shear, which is a shear in the horizontal. And the answers are that when you increase the shear, you increase the growth rate. And for a sufficiently large shear, you get growth of the magnetic field. And this is another picture of it. The growth rate increases with the shear, but not linearly, actually. And this is because the velocity field itself, in this case, depends rather strangely on the shear. And again, I want to show this picture, which you can't see. That's annoying. These are spectra. These are spectra. I'm not sure I can even tell you what they are now, which is which. Well, what I can tell you is that there is a mean field component now. So without the shear, it was like the problem I showed you the movies for. And in those movies, there was no mean component. And in fact, there was no large-scale field at all. When you add shear, you do get a large-scale component, which is perhaps not so surprising because there is a large-scale modulation of the flow on the scale of the shear. And that may be the answer, that you get large-scale coherence because you have large-scale variations in the parameters, not because you have some mean field effect. The alpha effect is as bad as ever. And so the shear itself doesn't change the flow in such a way as to make the alpha effect a better effect. So something else may be going on. We don't know what it is. And we've tried to understand, and again, I'm a bit short of time. We've tried to look at various aspects of the flows we get. So what we do is we solve the convection problem at high resolution. We solve it properly. Then at the same time, we filter the velocity field. So we take out bits of the field in Fourier space. And then we solve the induction equation for this new filtered field, but we solve it properly at high resolution. So we're really solving the induction equation, but the velocity field we choose is a smoothed version, in some sense, of the real convection. So that we can see which scales are important. And you can either remove modes with high wave number, or you can remove modes with low wave number, except for the shear. We have to keep the shear, otherwise there's no effect of the shear. So if you remove intermediate modes between the shear scale and some larger scale, then you've got a two-scale flow, large-scale shear, small-scale flow. You might think that the magnetic field produced in that way would be of mean field type, and you would say, yes, the alpha effect is right after all, as long as there's a scale separation. Well, here's the dynamo you get for the unfiltered flow. This is looking down from above, so the shear varies in this direction, and because it's rotating and sheared, conditions up here are different from conditions down here because the total vorticity is different in the two regions. Now, if you then scale then filter the flow by taking out the small scales, you get very similar form for the magnetic field confined to this top half. If you remove the intermediate scales and leave the shear, then you get very similar growth rates. All these growth rates which are plotted are quite similar to these. But the magnetic field is strong in the other half of the layer. This is a great mystery which we haven't got to the bottom of. And in fact, if you were to calculate nominally, you can't calculate, but if you were able to calculate the alpha effect, it would be strong here at the top, whereas the field is at the bottom. And so this is, we don't understand this. It doesn't seem to me that there's any true mean field processes going on here, even though it's clearly the case that there are small scales in the magnetic field which are much smaller than the cross-layer coordinate. So we don't think that you can construct an alpha effect model of this process which leads to fields like this. And we don't understand at the moment why this mode of growth should be so different from this mode of growth, even though the growth rates are all rather similar. That's quite interesting. So there's a lot of work to be done there. But again, we failed to come up with a problem where we can say, ah yes, the alpha effect is the right model to describe the growth of this field.
Shear is like differential rotation, really, isn't it?
Yes. Yes, it's
sort of you're looking for an alpha omega type dynamo.
You're definitely looking for alpha omega type dynamo, but we tried to model this with an alpha omega type model and it couldn't get it to fit. Absolutely, yeah. So this is something else. So this is my last bit. This is quite different because I've just done this work and I wanted to talk about it. So now, abandon alpha effect, all ye who enter here. This is all about bounds on flows. And I know there are one or two people here who know much more about this than I do, and this is all rather primitive. But I've been interested for some time in what's called the Arcontis dynamo. This is well, if you take a periodic box and you force a flow, in a sufficiently simple flow, I should say, because the full ramifications have not been explored, a fairly simple flow, at reasonably high Reynolds number and magnetic Reynolds number, you can get to a state where the velocity and the magnetic field are almost the same. If you look at this equation, here's the equation of motion with the forcing and the induction equation. So now this is non-dimensionalized. So F is a measure of the forcing. It looks peculiar, but you could also think of it as the Reynolds number. And so F is like the Reynolds number, and PM is the ratio of diffusivities. So eta over nu, or nu over eta rather. So you can see that if U and B are very similar, then actually there should be an F here as well. Sorry about that, there should be an F in front of this. If U and B are almost the same, then these two terms cancel, approximately. And if U and B are almost the same, then this cross product is very small. So you can see there's some asymptotic possibility here where that sort of alignment occurs, except, of course, in diffusive layers where these terms have to be taken into account. It's not entirely straightforward. But you can prove a few things in general, and then you can think about the conditions under which such solutions are possible. It's easy to find such solutions by choosing the appropriate form of F. I'm going to assume F is steady, by the way. So you could easily write down an energy equation by dotting this with U and dotting this with B. And when you do that, you find that all the difficult terms, all these terms, which are now cubic in the amplitudes, will disappear. They cancel out. There's energy, the Lorentz forces, and the induction force here, and this induction term in the induction equation, they all just transfer energy between the magnetic and velocity field. So they add up to zero. So you get a very simple result that you can bound the total energy above, because this thing is less than the average of U squared times the average of F squared to the half. And we've assumed that the average of F squared is 1. And so it's less than or equal to E. So we have this very nice upper bound on the magnetic energy. It has to be less than or equal to that. And in fact, there's a global upper bound, which is easy to write down. I'm sure many people have written this down. We can also, curiously, bound the magnetic energy from below. So you can multiply this equation by F, and then average. F is steady, remember. So the term in du by dt goes away, and you have a different exact equation here. And then by fiddling around and using upper bounding theories, you can write down another equation like this with the inequality going the other way now. And so now we can find that the magnetic energy squared is greater than something involving F and the kinetic energy. So we can put these two together. So I'm interested in the ratio of EM to E. So for the Arcontis dynamo, the ratio is 1. So let's write the ratio as k squared, and just for analytical convenience, just write g as 1 over the kinetic energy. Then you have these two inequalities, which now don't involve the magnetic field at all, only the ratio of energies here. So A and C are known numbers which you can calculate from F. A is the maximum of mod F, and C is it's to do with the gradients of F. It's greater than or equal to 1. So we have these two inequalities. This one does not involve PM, but this one does. But you can see that, I don't know if you can spot this, but in fact, these two inequalities together tell you that k squared can't be too large. K squared has to be less than this, but it also has to be greater than this. So these two curves intersect, so it can't go above where the curves intersect. And so we can work out the maximum possible value of k squared for any given f. And for the Arcontis dynamo, f looks like this. So it's very simple. It's one that's been done before. And so the maximum is root 2/3, and the I think that's right. Yeah, I'm sure that's right. And c is equal to 1, as it happens. And so for the Arcontis dynamo, k squared is about 1. And so we can, if we put 1 into this pair of inequalities, then we find that f has to exceed a certain number. And here it is. And what we find in our numerical computations is that for f is 100, okay, it's very hard to cover the whole parameter range. For f is 100, and PM is about 1/10. So that's Reynolds number. So the Reynolds number is 100, and the magnetic Reynolds number is 10. Then you're about on the boundaries of dynamo action. That's about right from this inequality. This gives the right order of magnitude for the minimum value of f. Now, as an alternative, we can do this. We can add and subtract the equations and derive equations of what we can call the Alsace variables, which is the sum and difference. So for the Arcontis dynamo, Z minus is very small, say, and Z plus is approximately 2u or 2b. So if we add and subtract, we have two equations here with plus and minuses, and you see they're in very compact form. It's rather beautiful. And especially when PM is 1, when this term disappears, they're sort of just very lovely pairs of equations. So we can dot these equations by z plus and minus respectively, and get, in the same sort of way as we did before, bounds on this quantity, which is the dissipation of these Alsace variables. So we have an inequality here which gives you a relationship between the dissipation due to d plus and minus and d minus and plus. So these are linked equations, and there are two of them. We can divide through. There are still two equations. So each of the d's has to satisfy an equation of this form. And you can see in the special case that PM is 1, that d plus or minus is bounded above. So that's one equation. Here's another equation. So this comes by multiplying those equations by f. So you get two more equations with the inequality. This is exact. Oh, sorry. You get two more equations. You get this. I'm not sure what that mod is there. But the inequality now goes the other way. So this is a lower bound on the d's, where you have this. I mean, I've been more generous here. For the Arcontis dynamo, this is 1. Oh, root 2, sorry. So for the Arcontis flow, we know V and U. So U is this. The notation I can see is slightly different from the previous bit, and I'm sorry about that. Here's F again, the same F. So we have these two inequalities, but we can use them together to get a bound on the ratio of these two. So for the Arcontis dynamo, R should be very small, or else very large, doesn't matter. And so how small can R be for a given value of H, which is a simple function of F? For PM is 1. And so for different PMs, we can plot these curves, which are derived from these two inequalities. And actually, it's quite interesting to see that when PM is very small, you might think you'd do better. The dashed dotted line is this one. And actually, if I've got it right, it seems quite hard to get quite very low values of R. I think this is quite a strong constraint here. It seems to be stronger than the other one. You can say, well, you can't have U very close to B if R is, you know, at 0.2. Obviously, you're some distance away. And you've, in fact, for small enough H, you can see you can't have an R-Contist type dynamo because the minimum of the ratio is not small. So this is giving some information as to the where these dynamos can be found. And we've done a lot of runs, but not enough really to put points on this piece of paper. But they are, of course, all the points we've found are in the right place. They don't violate the inequalities, but I can't tell you exactly how close they are. So one final thing, and it's been a long time I've been thinking about these problems. So for 33 years, I wanted to prove a result like this. And there's a paper I wrote in 1979 which didn't quite prove it. And it annoyed me enormously, and I realized 33 years later that I'd made a little mistake. In fact, really, I'd proved it all along. So here's the right version. This is in Poland. This is one of those meetings in Poland that Richard Herczynski used to organize. So I gave this talk. So I wanted to find a condition for an R-Contist dynamo based on a sort of energy argument. So here is an equation for the magnetic energy averaged in space but not in time. So these brackets are averages over space and time. But this is an average over just space, so it has a d by dt in it. This is completely standard, what I've written down here. And it just comes from the induction equation. And then I can bound this term in terms of the viscous dissipation. So this is all very standard use of the Schwarz inequality. And this term here can be further bounded in terms of the average of B squared and the averages of grad B squared by what I now know to be a Galliardo-Nirenberg inequality, but didn't 33 years ago. And the number S is just a number whose value I don't know. It's order unity. In principle, it can be calculated, but I haven't tried. So I've got this inequality, and I'm now going to define the ratio of the dissipation of B to B itself and write down an equation for the logarithm of the energy. The energy is not zero, so that's all right. And I found this inequality here using these results. And then I take the average in time, and I fiddle around again using Schwarz type inequalities. And this is where I made a mistake. At some point here, I lost my nerve and said, oh, you can't get anything in terms of this average. You can only take the peak of the space average in time. But that was wrong. Anyway, after a bit of simplification, you end up with something here times this. And for a steady dynamo, on average, this has to be at least as big as that. But Q squared, which is this ratio, can be shown to be bigger than 1. Because you're in a box of length side 2 pi, say. And so we have a bound on this, and that means that the viscous dissipation has a bound on it in terms of the forcing and the magnetic Prandtl number. So using that, and also assuming that we have an R-Contist dynamo, where the average, this is comparable to that, which we believe to be the case. I told you the energies were similar. It's a reasonable assumption that these are also quite similar. I haven't checked that, but I believe it's the case. Then if you go back to your energy equation, you have a bound, assuming this is true, you have a bound on the viscous dissipation involving the Prandtl number. That's approximately equal to that, which can be bounded like that because the average of F is 1. And so putting this together with this, we get this. And this formula looks the same, amazingly, as this. It's derived entirely differently. That's quite encouraging. So it suggests that this quantity PM, 1 over PM times 1 plus 1 over PM, is important. So it's important in 2 different ways. And so we're hoping that when we come to map out the parameter space, and this is a necessary condition for a dynamo action at all, but of R-Contist type, that we'll find that this quantity, this function of PM, is important, although the numbers here, it's not quite clear what happens to them.
It's simpler if you multiply it out, PM plus 1.
There's something wrong with this then. Oh, this should be what? This is 1 over PM. You're absolutely right. It's a misprint. This is 1 over PM. I think so. Yes.
Ah, right. Yeah. Okay.
Okay, I've come to the end actually. So just to sum up what I've talked about, and I'm sorry it's a bit of a mishmash. So the mean field formalism, which I talk about, gives attractive models, but they don't lead to quantitative predictions. It's impossible to know how to calculate alpha, whether it's a local function of B, whether there are bits that don't depend on B at all. It's an attractive model, and I think that's all you can say about it. You can put it into the equations and you get models that look like the sun. But whether you're learning anything, I don't know, but illustratively it's quite interesting. Dynamos at large Rm, it seems, with turbulent flows can't be characterized as alpha effect dynamos. Adding shear doesn't seem to help. It enhances dynamo action, but it doesn't seem, even now, to be of mean field type, but maybe we're in the wrong parameter range. And shear flow induced dynamos don't seem to be of the mean field type. That's what we said. And then finally, these dynamos that I've been working at with Dave Galloway only exist in a narrow range of parameters. But it turns out that even if you can't do the numerical computations, there are some rigorous methods which give quite good predictions of what's going on. Thank you.
Thank you, Mike. Are there any questions?
Many.
Well,
If I recall, last time I considered this field, there were some calculations that took a particular hotspot underneath the tachocline at the base of the convection zone. And for isolated hotspots, it might have taken 2 isolated hotspots, but you're not assuming any sort of homogeneous underlying velocity field to make the tachocline go unstable. You really assume it's just localized, that there are things that would drive a dynamo, at least for a short period of time, stronger than any sort of alpha model.
But
I don't know what became of that stuff, and I'm just wondering.
I'm not sure what became of that stuff. It's certainly true that if you have, I mean, the production of sunspots, it seems to me, is not in itself a large scale, I mean, it's larger scale than what we think of as mean field. The scale of sunspots is much smaller than the scale of the sun. So conditions, it's clear that conditions as a function of latitude vary. That's why you see sunspots at certain latitudes but not others. I don't find that surprising. What I find surprising is that the sun knows about the phase of the other hemisphere. That I find very interesting, and that's not fully understood. So there must be some global effect, even though the production of sunspots is probably locally energized.
Any possible estimates of the relation between grad v square and grad v square and the solar conditions?
grad U squared.
Yeah.
Yeah.
I don't think that's very easy. I mean, one can estimate sizes of fields. The biggest fields in the sun are on the smallest scales. Right, so all the dissipation is on the small scale. There is a large scale colloidal field, but it's very weak on average. Fluctuations dominate the mean. And that's another problem with the alpha effect. If to calculate the alpha effect, you have to assume that the mean dominates the fluctuations. But that's not true in the sun. It's quite plain that the fluctuations are enormous compared to the mean effect.
One thing is
You
that
don't really have to assume that.
Well, no, but there's a question about correlations and so on.
The
Yes.
equation for the fluctuating V, there is a particular integral, you might say,
Well, yes.
which is linear. And
Yes, I agree with that.
there's what I would think of as a transient, which may not be transient.
Well, yes. No, I can see in principle.
There are 2 parts.
Yeah, there are 2 parts. It's not. No, I agree with all that, and it's true that in principle, if there were not a small scale dynamo, you could make your way to calculate, even though the fluctuations dominate the mean. I agree with that. Yeah.
And the question I raised in Edinburgh was this: that if you're right and it really is small scale dynamo, then you still have the problem of explaining the large scale
You do.
solar field.
And that's what we're all.
It's a wide open problem.
It's a wide open problem. Absolutely, it's a wide open problem. I agree with you. And
That's why most of us work now in the Earth instead of the Sun.
because it's not a wide open problem.
At least it's low RM at the
Yes. I should say that in the Earth, I mean, numerical computations reveal behavior not unlike the Earth's magnetic field. And the magnetic Reynolds number on the scale of the convection is thought to be not too large. So some sort of mean field or averaging ideas are much more effective there. I think that's absolutely true.